I'll be demonstrating my final year project, which is called Authentication on Dedicated Hardware. So this project consists of using a system-on-chip device. So this device is the Ultra 96 V2, which has a built-in processor and field programmable gate array. This device is being used as an edge device to securely stream a camera as part of a surveillance and monitoring IoT system. So this is the device itself. So I have three connections. I have the power connection, a connection here to the host PC, which puts it onto the same local network. Wi-Fi can also be used, and then I have a USB webcam, which will be streamed across the IoT or the Internet of Things system. And then finally, there's also a micro SD slot. So this is what the board boots off of, and within this SD card is a pink image. So this pink image uses the pink framework. So the pink framework contains the Ubuntu 18.4 operating system and also a Jupyter web server to interface with the programmable logic of the device, and it's generally used for these devices in particular. So to program the programmable logic on the FPGA of this device, a bitstream is required, and this bitstream contains the RTL hardware design. And this design, it can't be read, it's encoded and it's unreadable. And if someone was to get the bitstream, it would be very hard to reverse engineer and to find the original design. So this bitstream was created using Xilinx's Vivado design suite. So here's an overview of the design. So in order to validate the key, a 256-bit symmetric key has been defined within this IP. So this IP was created using FADO HLS, and it also contains the functionality to authenticate and input symmetric key, so the user's key, basically. So this will get the data through an AXI interconnect, which through a master and slave port connects to the processor of the Ultra 96. So this is the Zynq UltraScale Plus MPSoC, and the data is will use a memory map, and through the AXI Lite interface will be able to interface between the IP and the processor and send data between the two. So I'll head over to the device now. So I'll be using SSH to log on, and it is also password protected. So this is the device here, alongside the Jupyter web server, which was mentioned before. There's also an MQTT broker, which is started on boot of the device. So this uses the MQTT protocol at the communication layer of this Internet of Things system in order to route data from the publisher, which will be this device itself. So this will publish the camera stream, and this will be published to a topic of which subscribers can subscribe to this topic and receive this data. So this is quite a lightweight protocol, and it's the optimal choice for this use case. In order to view this data as a subscriber, a Node-RED server is running on the host PC. So this is the PC back here, and Node-RED is frequently used in building IoT-based flows. In this case, a subscriber has been set up within this flow and is able to view the camera stream via an online dashboard. So this is the dashboard here. So the server is running at this address, so on the local address on port 1880. And as there's no camera currently initialized, this is blank. But if I go over to the device again, I'll just show you the config and everything that's set up here. So if I go into the config, this is where the user is able to define the parameters of the device. So the input device is -1. This is the credentials path. So this is the key that's validated. And there's also the MQTT settings, so whereabouts it will publish the stream to, the address and the port of the broker, which is again this device, so it's on localhost. And the bit stream, which conceals the key and the authentication method, is located here. So this is the validate key bit stream. If I open this file, you can see that it's completely unreadable, and therefore the key is secure and is able to ensure the origins and the integrity of the stream. So if I go to the credentials file that is being used, so I have two keys here. I have the credentials and also the unauthorized credentials. So basically a valid and an invalid key. So if I just open this, you can see that this is binary encoded also, and therefore unreadable. So the only place that actually contains this key in a readable fashion is within the bit stream when it was designed. So once it's been created, it is no longer in any readable form. So if I go over to the Jupyter Notebook here, this is where the functionality of the device can be configured. As of now, it has a invalid key set up. So if I just run this, you can see it's unable to authenticate the device, invalid credentials. So it basically takes the input key, writes it onto the memory of the FPGA, and then reads the output back once the IP determines whether it's correct or not. So just to show, if I go to the logs here, we can see that an error log has also been given to show that an unauthorized access has been attempted and the time of that access. If I go to the dashboard, you can see that it's not started. But if I now go to the config and update the location of the file to a correct key right here, and I'll just restart this kernel. Right, so now if I attempt to run this again, it will again write the credentials to the FPGA, and we can see that the device authenticates successfully. It has also written its log, and it has begun sending the stream to the camera. So now if I go back here, we can see that the camera stream has started. So now all the subscribers can see this feed, and the origins of where it was sent from can be assured through authentication via the dedicated hardware, and specifically the Ultranight 6 V2.